Hi, I'm Jean-Pierre Williams, and I'm a research scientist here in the Department of Earth and Space Sciences. Much of my research involves actually heat flow in planets, either from the interior of planets, as planets evolve and lose their heat, driving tectonics and volcanism at the surface, or looking at heat flow in the surface layer of the regolith due to solar forcing. The main project I'm working on right now is working on the Diviner Lunar Radiometer Experiment, or Diviner for short, which is an instrument on the Lunar Reconnaissance Orbiter currently at the Moon. And what this instrument does is look at light coming from the surface in several different spectral channels. The ones I look at are mainly 7 channels in the infrared. So we're looking at infrared light that is emitted from the surface, and this gives us an idea of the surface temperature in much the same way that an ear thermometer works. If you stick an ear thermometer in your ear, it's looking at the infrared emitted by the eardrum and gets a temperature. And we do much the same thing, but we look at the surface of the Moon. And so this gives us an idea of the thermal environment, which is one of the main goals of Diviner. And what we find is that the surface temperatures are actually quite extreme, and this is due mainly to the fact that there isn't ocean or atmosphere to buffer surface temperatures. And so what I try to do is understand how that regolith can store and exchange heat, and also how things like rocks that have different thermophysical properties, how they affect our temperatures. Rocks can store a lot more heat than the surrounding regolith, which is very low density and fluffy, and so rocks can store a lot more heat at night and give us a much warmer surface temperature. And so we're trying to understand how rocks of different sizes affect our measurements. Most of my Mars research has been mainly looking at heat flow from the interior of the planet, so trying to understand, for example, under what conditions was Mars able to generate a magnetic field. We know within the first 500 million years of its formation it had a magnetic field similar to the Earth, and that magnetic field shut off at some point. And so I've been looking at the energetics of the core, and also trying to understand how heat flow affects what we call the lithosphere, or that rigid, colder upper boundary of the planet, and how, looking at both topography and gravity data, trying to understand how topography is basically supported. And that tells us something about the heat flow of the planet as well, and its thermal history. Another aspect of my research on Mars actually focuses on cratering and trying to understand the cratering rate and the crater population. And we care about this because craters tell us something about the age of the geologic units. So the longer surface sits there exposed, the more craters it accumulates, and that tells us something about its age. Now we have samples from the Moon, from Apollo, that we've radiometrically dated, and so we can tie absolute ages to populations of craters on the surface, and then we can relate those populations on the Moon to other bodies in the solar system. Planetary scientists, we really step back and look at all the planets and try to understand processes that are common to all the planets, and I think ultimately this helps us understand our own planet. And of course it's important for a lot of reasons to understand our own planet, but also for exploration purposes. As we push our frontiers outward and we start to explore the solar system, it's really important to try to understand our neighbors as much as possible.